This video is about the collision theory, and in your note packet, you should go to the section where it says chapter 14.5, temperature and rate. And think about the things that we've already learned. We already know that if you increase temperature, the reaction's usually going to speed up or go faster. And we're going to talk about why that happens in this video. Okay, now we have to keep in mind that every reaction has a rate law. Now that rate law is written generically as rate equals some constant K times the concentration of A to a power of M times the concentration of B to the power of N. N. A and B are reactants, and M and N are experimentally determined. Now, if temperature goes up, concentration is not affected. So if the concentration is not affected, but the rate is still going to go up, if you increase rate, and these things are not being affected at all, it must be K that goes up. So if a reaction happens at one temperature, it has one K value. If it happens at a different temperature, its K value is different. So K is a reaction constant, a rate constant, but it is based on temperature. That's important to understand. Now, the collision model is going to explain why things react the way they do. So there's a few things you need to understand. In order for molecules in a chemical reaction to actually react, they have to bump into one another. They have to collide. And rates of reactions would be affected by two things we've discussed already. One is concentration, and the other one is temperature. If you just think about this for an example, if you put more molecules in a container, you are increasing the concentration. Now, when you have more molecules in a container, they are more likely to collide because there's just more things to bump into. Think of it like cars on a freeway. If you are in heavy traffic, you are more likely to have an accident just because there's more cars for you to bump into. Okay? When there's people in the hallway, crowded hallways, you're more likely to bump into other people because there are people in your way versus when you're in the hallway alone. Okay? Same thing is true with temperature. If you increase the temperature, okay, without increasing concentration, so think of these separately. If you increase the temperature, now the molecules that were there are just going to move faster. So if you picture yourself walking through the hallways of school between classes, and now picture everybody running, okay, if everybody speeds up, you are more likely to bump into each other more often if you're running than if you are walking at a normal pace. Same thing with cars. When you're driving on the freeway, you are more likely to have an accident if you are going at a higher speed. You are more likely to collide. So that's why concentration and temperature affect reaction, and here's your molecular explanation. So this is basically the same thing I just got done saying. Molecules collide to react. So the greater number of collisions, the greater the rate of reaction. Now we can cause more collisions by doing one of two things. We can either increase the concentration. If we increase the concentration, we've put more molecules in the container. When you have more molecules, there's a greater probability of colliding, and so therefore the rate would go up. When you raise the temperature, the number of molecules aren't changing, but you're asking them to move faster. So when they have more kinetic energy, they are more likely to collide into one another. Now, the important thing to remember is that not all collisions will result in product formation. So just because molecules bump into each other does not mean that they will automatically change into the product. Only a small fraction actually do. And there are two things that affect it, but three things must occur, okay? So three things that have to occur for the reaction to actually happen. So the collision to result in a change. Number one, the reactant molecules have to collide first and foremost, okay? So we kind of understand that. But the two things that are important are, not only when they collide, they have to have enough energy. So think of it like a car accident. If you are going to have an actual collision that results in damage, you have to be traveling with enough energy to hit somebody and change the shape of the car. Okay, with cars it's not that hard, but with molecules they have to have enough energy to actually do some damage, change them. And then secondly, they have to collide in a way that actually leads to the product formation, the rearrangement that you want. So here are some pictures to show you what I'm talking about. You might want to sketch these in your notes. I've left you some space. So let's picture the reaction where we have NO2 reacting with CO to form NO and CO2. So really what we need to do is have one O leave the NO2 molecule and join up to the CO2. Now you guys should know when we draw this that CO2 looks like this. So the arrangement we need is for an O to be next to a C in order for it to switch places, okay? So if you look at scenarios A and B, okay? In A here, we have the C and the O, and they are going to collide with the NO2 molecule. But if you look right here, the O's are what's going to bump into each other. That's not what we want as a product. So this results in no reaction. In setup B, the carbon monoxide is still set up like this. The NO2 is flipped upside down, but still we're set up so that oxygen will bump into oxygen. That's not what we want for a product, so that won't result in a reaction. Now, with C and D, you can see that one will result in no reaction, but finally in D we will. In C, we flipped our CO around, so now we have the right orientation for the carbon monoxide, but in this case, the N is what's next to the C. That's not what we want to bond, so this will have no reaction. The only reorientation that works is when that C from the CO is next to the O from the NO, and what will happen is this guy can then leave, and you'll get NO and CO2. So hopefully you understand there are two really important factors. One is that they have to have the right orientation, and the other one is that they have to have enough speed to actually react. So let's look at D again. Even if this happens, even if D has the correct orientation, okay, the orientation is perfect. That's a good thing. That will react. But they have to have enough energy. We call that a minimum amount of energy, and that's going to lead us into our next topic. So orientation is one thing, and the minimum amount of energy is another. We assume that all molecules have to collide to react totally. Okay, so in our next video, we'll talk about that activation energy.